Good morning. Welcome to everyone joining this meeting of the Developmental and Reproductive Toxicant Identification Committee, or DARTIC. This meeting is being held in person and virtually. My name is Dr. Kanan Krishnan. I'm the Assistant Deputy Director for Scientific Programs and the Acting Deputy Director for Scientific Programs at the Office of Environmental Health Hazard Assessment, or WEHA. WEHA is a department within the California Environmental Protection Agency and is the lead state agency for the assessment of health risks posed by environmental contaminants. Lauren Zeiss retired as WEHA's director in June of this year, and Dr. Dave Edwards, our Chief Deputy Director, is the acting director of WEHA. And Dave could not be here in person as he's not feeling well, so I will be acting in his capacity at this meeting. As we get started, just a couple of housekeeping items for those attending in the room here in Sacramento. The emergency exits are the two double doors directly in the back where you entered the room, and at the front of the room to the left under the lighted exit signs. You can access the restrooms by going out the back double doors, turning left, and walking to the end of the hall. We have 3 newly appointed members of the committee, and I'll be introducing and swearing them in shortly. Our main agenda item for today is the consideration of bisphenol S, or BPS, for listing as a male reproductive toxicant under Proposition 65. BPS is on the Proposition 65 list for reproductive toxicity based on the female reproductive endpoint. For the final agenda item, staff will present updates on various Proposition 65 regulatory and other activities. We will take a 45-minute break for lunch around noon and take a short 15-minute break sometime in the afternoon. And this meeting is being recorded and transcribed. The transcript will be posted on WEHA's website. During this meeting, there will be an opportunity to provide oral public comment on the BPS item. Individuals who are in person and wish to make an oral comment at today's meeting are asked to fill out a blue comment card and give them to WEHA staff. The blue comment cards are located in the back of the room. When called by the chair, please approach to the microphone. Please state your name, affiliation, and provide your comment. Those who are joining us virtually and wish to make an oral comment at today's meeting are asked to join the Zoom webinar. Information on how to join via Zoom is shown on the slide. Go to bit.ly/register.ic 2024 and register for today's Zoom webinar. You will receive a link to join the webinar at the end of the registration process. And if you provided a working email address, you will also receive an email with a link to join the webinar. Zoom users can also access closed captioning by clicking the CC button on the bottom panel of the screen. Those of you watching by Cal EPA webcast will be able to watch the meeting, but you need to join the meeting by Zoom to speak. When requested by the chair, individuals on Zoom may queue to provide oral comment by using the raise hand function. When your name is called during the opportunity for public comment, you will be prompted to unmute yourself. Please unmute yourself, state your name and affiliation, and provide your comment. If you would like to present slides during your public comment and have not already sent them, please email them now to p65public.comments@weha.ca.gov. Public comment will be limited to 5 minutes per commenter. Before we get started, I'd like to introduce 3 new members of the committee and then swear in. Starting with Dr. Martin Kulte. She has been Associate Professor of Pharmacology and Pharmaceutical Sciences in the School of Pharmacy at the University of Southern California since 2016. She was an Associate Professor for the McGill University Faculty of Medicine from 2007 to 2016, and at Georgetown University from 2005 to 2007. She was an assistant professor at Georgetown University from 1990 to 2005. Dr. Kulte is a member of the Society of Toxicology, American Society of Andrology, Society for the Study of Reproduction, and the Endocrine Society. Dr. Kulte earned a Doctor of Philosophy degree in molecular chemistry and a Master of Science degree in molecular and cellular biology from Université Grenoble-Alpes. She earned a Bachelor of Science degree in animal physiology from Université Claude Bernard. Welcome to the committee, Dr. Kulte. Dr. Sandy Ha has been an assistant professor at the University of California, Merced since 2017. She was an Intramural Research Training Award postdoctoral fellow at the National Institute of Child Health and Human Development from 2015 to 2017. Dr. Ha was a predoctoral fellow at the University of Florida from 2011 to 2015. She is a member of the American Public Health Association, Society for Epidemiologic Research, Society for Pediatric and Perinatal Epidemiologic Research, and the National Faculty of the National Board of Osteopathic Medical Examiners. Dr. Ha earned a Doctor of Philosophy degree in epidemiology from the University of Florida, a Master of Public Health degree from the University of Florida, and a Bachelor of Science degree in biology from the University of Washington. Welcome to the committee, Dr. Ha. Thank you. Dr. Kim Hurley has been an adjunct professor for the School of Public Health at the University of California, Berkeley since 2009. She has also been Associate Director for Health Effects at the Center for Environmental Research and Children's Health, School of Public Health at the University of California, Berkeley since 2004. Dr. Hurley is a member of the International Society for Children's Health and the Environment, International Society for Environmental Epidemiology, and the International Society of Exposure Science. She earned a Doctor of Philosophy degree in epidemiology from the University of California, Berkeley, a Master of Public Health degree in maternal and child health from the University of California, Berkeley, and a Bachelor of Arts degree in anthropology from Vassar College. Welcome to the committee, Dr. Hurley. I will now lead them in the oath of office. New members, you will first be asked to say "I" and then state your name. You may choose to solemnly swear or solemnly affirm the oath. Okay. Stand up. I would invite you to stand up and take the oath. I state your name. Do solemnly swear or affirm that I will support and defend the Constitution of the United States and the Constitution of the State of California against all enemies, foreign and domestic, that I will bear the true faith and allegiance to the Constitution of the United States and the Constitution of the State of California, that I take this obligation freely without any mental reservation or purpose of evasion, and that I will well and faithfully discharge the duties upon which I am about to enter. Congratulations. Thank you. We are honored to welcome you to the DARTIC committee. Your deep understanding of reproductive toxicity and contributions in your fields will add to this esteemed body, which makes the state of California a leader in identifying reproductive toxicants and protecting people in the state from them. Now, I'm pleased to introduce the other members of the committee that are present today. And I will note that Drs. Baskin and Hertz Picciotto are not able to join us today. Okay. As I introduce you, please state your name and affiliation. Dr. Patrick Allard.
Yeah, good morning. Patrick Allard from UCLA.
Dr. Diane Ouyang Kim.
Diana Al-Young Kim from Genentech.
Carrie Breton.
Carrie Breton from USC.
Our committee chair, Dr. Ulrika Luderer.
Ulrika Luderer, University of California, Irvine.
Dr. Isaac Pesa.
Isaac Pesa, Emeritus, UC Davis.
Dr. Charles Plopper.
Charles Plopper, UC Davis.
So welcome, committee. Really appreciate you taking the time to provide your advice and judgment at this meeting. Now, let me introduce WIHA staff. For those of you in the room, I invite you to raise your hands. And for those joining via Zoom webinar, I invite you to turn on your camera. Thank you. From the Reproductive and Cancer Hazard Assessment Branch of WIHA, Dr. Martha Sandy, the branch chief. Dr. Francisco Moran, section chief of the Reproductive Toxicity, Toxicology and Epidemiology section. Thank you. Staff of the Reproductive Toxicology and Epidemiology section that are joining us today are Drs. Faye Andrews, Marlisa Campbell, Erndelker, Farla Kaufman, Yesaman Nicknam, Sarah Park, Sarah Saucier, Gabrielle Tuckman. And from our Office of External and Legislative Affairs and Proposition 65 Implementation Program, Tina Cox, Senior Environmental Scientist and Section Chief of the Proposition 65 Implementation Section. Tina is also acting for Amy Gilson, WIHA's Deputy Director for External and Legislative Affairs. Kiana Wagafi, Environmental Scientist, Proposition 65 Implementation Program. Esther Braz Ochoa, she's not here in person today. She's an analyst with the Proposition 65 Implementation Program. And Julia Deloff, Julia, Senior Environmental Scientist with the Proposition 65 Ombuds person, her first committee meeting. Okay. Now, I'll turn to Christy Morioka for some introductory remarks about Bagley-Keene and other legal issues related to today's meeting. Christy?
There we go. It's good to see everybody here today. So I'm Christy Morioka. I'm one of the lawyers here at WIHA Legal. I just had a few points to make. Please feel free to ask me any questions during this meeting. I'll be here the whole time. First, a reminder that the Bagley-Keene Open Meeting Act applies to this meeting. The goal of the Bagley-Keene Act is to promote transparency. So for the committee members, please remember that all discussions and deliberations about agenda items need to be conducted during the open meeting, not on breaks, lunch, or with individual members of the committee on or offline, and that includes via phone, email, chat, or text messages. And second, all experts serving on this committee have participated in mandatory ethics training and have disclosed any actual or potential conflicts of interest, including any relevant ex parte communication about the subject matter. And last, at today's meeting, you will be considering adding an additional reproductive toxicity endpoint to the listing of bisphenol S. OEHA takes no position regarding whether a chemical or additional endpoint should be listed, though staff are available to answer questions or locate information if you need it. The governor appointed you because of your scientific expertise to be the state's qualified experts on the reproductive toxicity of chemicals. There is no need for you to feel compelled to go outside that charge. For example, you need not consider whether a warning may be required for an exposure to a chemical or any other consequences of that listing. This committee has maximum flexibility in evaluating all pertinent scientific information in making a determination and can consider human, animal, mechanistic, or other data in deciding whether a chemical has been clearly shown through scientifically valid testing according to generally accepted principles to cause reproductive toxicity. If you need more information, need more time to consider the evidence, or discuss it further before you take a vote on a listing, there is no requirement that you make a decision today. For example, you may table the decision and take it up again at a future meeting. Feel free to ask clarifying questions of me or any of the other OEHA staff during the meeting. If we don't know the answer to your question, we will do our best to find it out and we will report it to you. Does anybody have any questions? Thank you.
Thank you, Christy. Now I'll turn the meeting over to the DARTIC Chair, Dr. Luder.
Thank you, Conan. Good morning and welcome to the committee members, as well as all the members of the public who are joining today, either in person or remotely. We're now ready to move on to the next agenda item. So the agenda item is, obviously the overall agenda item is consideration of listing bisphenol S for the male reproductive toxicity endpoint under Proposition 65. And I'm going to turn things over now to Dr. Francisco Moran, who is the chief of the Reproductive Toxicology and Epidemiology section, to begin. Dr. Moran.
Thank you, Dr. Luderer. Good morning, everybody. Relevant information has been reviewed and considered by OEHA for this year's Hazard Identification Document, or HID, that is on the evidence of male reproductive toxicity of bisphenol S, or BPS. In the last year meeting, BPS was considered for female reproductive toxicity, and it was added to the Proposition 65 for that endpoint. This document was released for public comment, and no substantial comments were received. The document and the cited references were provided to the DARTIC for consideration for today's meeting. This presentation is a brief overview and will not cover every finding discussed in the HID. I will start. It's not working?
A little
There, good, thank you.
closer.
Perfect.
Pancho, a little closer to the mic, or move the microphone closer to you.
Closer to me?
Yeah.
Oh, okay, sorry, thank you. Perfect. Okay, so this presentation is a brief overview and will not cover every finding discussed in the HID. I will start with the brief background information, then we will present results from animal and mechanistic studies, and then the epidemiologic evidence to finish with an integrative summary. I would like to acknowledge that this work was a group effort from the staff in the reproductive toxicology and epidemiology section. Here is the chemical structure of BPS and its structure analog BPA. Here is a summary of what was already presented to you last year on BPS use, production, and exposure. Some increases in BPS productions are associated with regulations on BPA by California in 2011 and by the FDA in 2013. Since that time, manufacturers have been gradually replacing BPA with BPS in consumer products. As such, exposure to BPS has increased, and studies from Biomonitor in California show detection frequencies up to 77% in California residents. Using a systematic approach, we conducted literature searches on the developmental and reproductive toxicity of BPS. We use HOG as a tool for a multi-level screening of literature search results. For these documents, we focus on literature relevant to male reproductive toxicity, where the last comprehensive search was in January 2024. Following oral exposure, BPS is rapidly absorbed. It is distributed throughout the body and likely undergoes enterohepatic circulation. It has been detected in human media, including seminal fluid. In male rodents, BPS has been reported in several tissues with high concentrations in kidney, liver, and plasma. BPS goes under metabolism by conjugation, both sulfonation and glucuronidation, and by hydroxylation in human and rodents. It is excreted in urine, bile, breast milk, and feces. The half-life in humans has been reported to be between 7 to 9 hours, and in male rodents between 3 to 12 hours. Now, Dr. Sarah Park will present the evidence on BPS and male reproductive toxicity from studies in animals. Thank you.
Thank you. We will briefly highlight the male reproductive system. The core function of the male reproductive system is to support the development, proliferation, and transport of the male reproductive cells called spermatozoa or sperm. Sperm develop from spermatogonia in a process called spermatogenesis. This occurs in the epithelium of the seminiferous tubules of the testes and is supported by the somatic Sertoli cells and interstitial cells located in the space between the seminiferous tubules, including Leydig, peritubular, vascular, and immune cells. Sperm undergo maturation, gain motility, and fertilization capacity, and are stored in the epididymis. They travel through the vas deferens and are combined with fluid from the seminal vesicles, prostate gland, and other glandular secretions, which together comprise semen. This process is tightly coordinated and supported by the hypothalamic pituitary axis and autocrine and paracrine signals. OEHA considered data from studies that evaluated molecular, cellular, tissue, and organ-level effects of BPS exposure on male reproduction in multiple species. This section summarizes the animal findings. We will present the evidence of BPS-mediated effects on spermatogenesis in the seminiferous tubule environment, sperm parameters, effects on other organ weights or histology, and reproductive performance. Microscopy images presented herein are examples from the animal studies in the HID, and in this section, all reference studies orally administered BPS except for one study that administered via subcutaneous injection and is abbreviated in the slides as SC. The specific topography and interactions of germ cells in the seminiferous epithelium are represented as stages of the spermatogenic cycle. Histologic analyses of these stages can provide insights into perturbations to spermatogenesis, including the abnormal absence or presence of germ cell types and alterations to histoarchitecture. In this example image, BPS exposure disrupted the epithelial transport of elongated spermatids in vesicles. Instead of lining the seminiferous tubule lumen, spermatids were embedded in the epithelium. Meanwhile, vesicles were located near the lumen instead of in the basal epithelium. BPS-mediated effects on spermatogenesis were observed in both rodents and zebrafish and included inter- and transgenerational effects. For example, increased germ cell apoptosis was observed in gestationally exposed mice, and altered proportions of specific stages in the spermatogenic cycle were observed in the offspring and great-grand-offspring of treated dams, and in mice treated postnatally or during adulthood. In zebrafish, sperm chromatin condensation, or pycnosis, and spermatid leakage were observed in the grand offspring of treated F0 zebrafish. Hypospermatogenesis, or reduction in germ cell numbers, was observed in multiple studies, including decreased meiotic recombination of pachytene spermatocytes occurring during the third phase of meiotic prophase 1 and decreased spermatozoa in mice, decreases in all germ cell types in rats, and decreased germ cell numbers in hamsters. Meanwhile, increased spermatogonia and spermatocytes, but decreased spermatozoa were observed in the offspring and grand offspring of treated F0 zebrafish. BPS exposure also affected the histoarchitecture of the seminiferous tubules, including decreased epithelial height in both mice and rats, and decreased tubular diameter in rats. This histology section of mouse seminiferous tubules shows thinning of the epithelium with BPS exposure. Increased vacuolization was observed in mice, rats, and hamsters in the epithelium, germ cells, Sertoli cells, and mitochondria. This close-up view shows the presence of a vacuole in the seminiferous tubule epithelium of a mouse. Effects on the interstitium, the space between the tubules, included changes to the area of the interstitial space and appearance of congested interstitial arteries in rats. This image of a testicular section shows an increase in the interstitial area along with Leydig cell damage. There were exposure-mediated effects on the interstitial cells, including Leydig cell damage, atrophy, and decreased Leydig cell numbers in rats and hamsters, and overall interstitial cell losses in zebrafish. From the seminiferous tubule lumen, sperm are transported to the epididymis where they undergo maturation. Several studies assessed the effects of BPS on sperm parameters and reported consistent effects of BPS exposure on sperm count, daily sperm production, morphology, and motility. Decreased sperm count was observed in mice, rats, hamsters, and zebrafish, with exposure occurring across life stages. Decreased daily sperm production was reported in all of the rat studies that assessed it, and altered morphology of sperm was observed in both mice and rats. Observations included the presence of sperm with no hooks, double heads, and banana-shaped heads. Decreased sperm motility was observed in several studies in mice and rats with exposure occurring across life stages, and in one mouse study in the great-grand offspring of exposed dams. Changes in male reproductive and endocrine organ weights may reflect underlying physiological alterations. Several studies in rodents assessed the effects of BPS on organ and tissue weights and histopathology, and overall results were mixed. While results were mixed for testicular, pituitary, and thyroid weights, when effects were reported for other reproductive organ weights, the direction of effect was consistent, including decreased epididymal weight, seminal vesicle weight, and prostate weight, all in rats, decreased gonatosomatic index in rats and zebrafish, and increased adrenal weight in rats. Histopathological observations of glands involved in male reproductive function included increased adrenal hyperplasia and/or hypertrophy, and in the mammary glands, multifocal or diffuse atrophy in rats. The mammary glands are estrogen-sensitive tissues, and in males, morphological changes to mammary glands may indicate altered hormonal response. One study in mice assessed mammary gland effects and reported changes to the size of the mammary epithelial trees, and one study in gerbils reported alterations to ventral prostate histoarchitecture and hyperplasia, with no effects on prostate weight. The image on the left are ductal trees from the left and right mammary glands of 9-week-old male mice. Larger epithelial trees are observed with BPS exposure. The image on the right shows histopathological and structural alterations in the ventral prostate of BPS-treated gerbils, including increased tissue relative frequency of the epithelium, muscular and non-muscular stroma, decreased luminal compartment, and hyperplasia. Two studies in BPS-treated male mice mated with untreated female mice assessed reproductive performance. One study reported increases in the number of days to successful mating, and in male mice exposed during lactation and subsequently mated with untreated females, there was a decrease in zygote cleavage rate, as shown in this image, and a decrease in the number of blastomeres per blastocyst. And now, Dr. Sarah Saucier will discuss the mechanistic evidence for BPS-mediated toxicity on male reproduction.
Thank you, Dr. Park. In vivo and in vitro studies of BPS toxicity in the male reproductive system identified evidence of oxidative stress, genetic damage, apoptosis, epigenetic alterations, and endocrine disruption, among others, most of which are features outlined by the key characteristics of male reproductive toxicants. BPS consistently exhibited 7 out of 8 of the key characteristics of male reproductive toxicants, or KCs, which are 8 biological markers that are frequently exhibited by exogenous agents that cause male reproductive toxicity, and are a tool used within our hazard identification process. We did not identify studies in our search that specifically examined the induction of inflammation, KC8. Here we provide a snapshot of the systems with findings that can be classified as mechanistic evidence of toxicity. As you can see, mechanistic evidence was identified in a variety of systems treated at a wide range of doses and over several exposure periods and durations. These included in vivo systems examining treated mice, rats, hamsters, gerbils, zebrafish, and guppies, and in vitro systems including testicular explants, primary germ and somatic cells, and various cell lines. I will now provide a brief overview of the major mechanistic findings, describing in vivo evidence first, followed by in vitro in the order of human, mouse, rat, other rodent, and non-mammalian for each effect. There is abundant evidence that BPS induced oxidative stress in male reproductive tissues and cells. Oxidative stress occurs when there is an imbalance of reactive oxygen species and antioxidants. Although physiological levels of reactive oxygen species play an important role in the normal function of the male reproductive system, increased levels that lead to oxidative stress can overwhelm cellular and tissue antioxidant capacity and contribute to pathological effects. BPS increased the levels of reactive oxygen species, including peroxide species and superoxide radicals, in testicular tissue, sperm, and Leydig cells in rodents. Lipid peroxidation was also increased in testicular tissue, sperm, and Leydig cells in rodents. BPS altered at least one key component of the antioxidant system in several studies. Most effects demonstrated an increase after short exposure durations, likely as an initial response to an oxidative challenge, and a decrease after longer exposure durations, potentially demonstrating an overwhelmed antioxidant system. Antioxidant molecule levels and enzyme activities, including glutathione, glutathione reductase, superoxide dismutase, glutathione and general peroxidases, and catalase were increased after exposure durations ranging from 2 to 24 hours, and then decreased for exposures ranging from 1 day to 48 weeks in rodent testicular tissue, sperm and Leydig cells, and human prostate cells. BPS altered the expression of oxidative stress-related genes in mouse testes and bovine sperm, and proteins in rodent testes. There was evidence that BPS induced markers of genetic damage in male reproductive tissues and cells. Toxicants can induce genetic damage to sperm and other male reproductive cells directly or indirectly through processes such as oxidative stress. Sperm are particularly vulnerable to DNA damage due to a variety of natural characteristics, including a lack of DNA repair capacity. BPS increased the DNA fragmentation index in rat sperm and 8-hydroxy-2-deoxyguanosine, a marker of oxidative DNA damage in rodent testes. Evidence of DNA damage identified by the COMET assay were found in rat sperm and human prostate cells. Phosphorylated H2AX, a marker of DNA double-strand breaks and genomic instability, was increased in mouse testes, spermatogonial cells, and zygotal tissue and blastomeres produced by treated males and untreated females. Additionally, the expression of a DNA damage repair gene was decreased in human prostate cells. BPS induced apoptosis in male reproductive tissues and cells. Apoptosis is a programmed cell death that may occur as part of the normal life cycle of a cell or as a self-destruct process during injury. It has both beneficial and detrimental consequences in the male reproductive system. Apoptotic alterations in germ and reproductive somatic cells can adversely affect sperm parameters and reproductive capabilities. Evidence of BPS-induced apoptosis included increases in DNA fragmentation, apoptotic index, and apoptosis rate in mouse germ, sperm, and late egg cells, respectively. Apoptosis-related genes were altered in mouse testes and proteins in rodent testes, human prostate cells, and mouse late egg cells. BPS induced epigenetic alterations in male reproductive tissues and cells. Epigenetics refers to the regulation of gene expression through heritable and stable modifications that do not involve changes to the DNA sequence. Epigenetic modifications are essential to various aspects of male reproduction, including sperm production, and interference of environmental toxicants can not only have direct detrimental effects on the male reproductive system, but also has the potential for inheritance across multiple generations. Global DNA methylation was altered in zebrafish testes exposed directly or transgenerationally in mouse spermatocytes, excuse me, and an mRNA adenosine modification was decreased in mouse late egg cells. There were changes in the expression of genes involved in epigenetic processes in the testes of rodents and zebrafish exposed directly and/or transgenerationally, and proteins in germ and Sertoli cells of mice exposed directly and/or transgenerationally and rat sperm. There is substantial evidence that BPS induced endocrine changes in male reproductive tissues and cells. Several male reproductive toxicants are known to cause adverse effects on male reproductive function by interfering with one or more components of the endocrine system. This may be done through the agonism or antagonism of receptors, changes in receptor levels, or altered concentrations of hormones in circulation or organ tissues. Cholesterol, a precursor of all sex steroids, was decreased in rats. Gonadotropin levels were decreased in rat plasma. BPS consistently altered testosterone levels, including in rodent and zebrafish blood, human, rodent, and zebrafish testicular tissue, whole zebrafish, and rodent late egg cells. Estradiol levels were also consistently altered, including in rodent and zebrafish blood, mouse urine, and rat and zebrafish testicular tissue. BPS also increased the estradiol to testosterone ratio and aromatase activity, an enzyme responsible for converting androgens into estrogen, all in zebrafish. Additionally, BPS altered hypothalamus pituitary gonadal axis signaling in rats and mouse spermatocytes, and thyroid hormones and receptor levels in mice and zebrafish. BPS decreased serum melatonin in hamsters, a hormone that influences testosterone synthesis and testicular function, and increased progestin levels in mouse late egg cells. Further, BPS altered the expression of several endocrine-related genes and proteins, including those involved in steroidogenesis, steroidogenic regulation, steroid receptor production, vitellogenin, a marker of estrogenic endocrine disruption, and thyroid hormone and melatonin receptors in rodent testicular, mammary, and prostate tissues, various zebrafish and guppyfish tissues, and/or mouse sperm and somatic cells. Lastly, there were several additional reports of mechanistic evidence that are briefly highlighted here, including disruption of the blood-testis barrier, cell cycle and proliferation interruption, such as interrupted mitotic progression in spermatogonial cells, organelle and cytoskeletal effects, such as impaired mitochondrial function, and spermatogenesis-related molecular modifications, such as diminished processes involved in sperm motility, capacitation, and acrosome reaction. Thank you. I will now turn the presentation over to Dr. Farla Kaufman, who will summarize the epidemiologic evidence of BPS toxicity in the male reproductive system.
Thank you, Dr. Saucier. I will now review the epidemiologic studies. Several exposure characteristics influence a study's ability to detect an association if one exists. In this data set, BPS exposure varied across studies. There was considerable variation in the limit of detection or quantification, and thus in the ability to detect BPS in the samples. The percentage of samples with BPS levels above the limit of detection also differed across studies. Median exposure levels also varied considerably. However, the variability in BPS concentrations within studies was limited. The outcomes in the included studies were semen quality, reproductive hormones, time to pregnancy, and male offspring reproductive development. All except 2 studies used a cross-sectional study design. As you see on the screen, these are the specific outcome measures under each category. I will present the findings for BPS exposure associated with semen quality and reproductive hormones. There was only 1 study of time to pregnancy and 1 of male offspring reproductive development, neither of which observed any significant association with BPS exposure, so I will not be discussing these last 2. In the following slides, statistically significant results are bolded. Starting with sperm concentration, 2 of 5 studies observed significantly lower concentrations associated with BPS exposure. Both of these studies compared men with BPS above and below the limit of quantification or detection. In the second study, the difference in sperm concentration was even larger in men with a higher BMI. 3 studies observed no significant associations. One of these studies had extremely low BPS levels, with another having 35% of participants with BPS levels below the limit of quantification. 2 studies also observed significantly lower sperm count. A relative risk of 0.85 per 10-fold increase in seminal plasma BPS was reported in 1 study, while the second study only saw a significant decreased sperm count in men with a higher BMI. 3 studies did not observe any significant associations with sperm count. Sperm motility was examined in all 5 studies, 2 of which observed significantly lower progressive and total motility. 1 study observed increased odds of below reference progressive and total motility. A significant inverted U-shaped curve was seen for both measures of motility. In the second study, total motility was lower at a p-value of 0.06 in men with detectable versus non-detectable BPS, and significantly lower in men with a higher BMI. 3 studies did not observe significant associations. Significantly lower ejaculate volume associated with BPS exposure was observed in 3 studies. 1 study compared detectable BPS concentrations to non-detectable concentrations, with another observing a significant 13% decrease in volume between the 3rd and the 1st quartile of exposure. The 3rd study saw a 9% decrease in volume per 10-fold increase in seminal plasma, BPS concentrations. A 4th study reported non-statistically significant lower ejaculate volume, as well as decreased odds of having ejaculate volume greater than 1.5 milliliters. Sperm morphology was examined in 5 studies, none of which observed significant associations. Similarly, no associations were observed for 2 studies of DNA fragmentation and 1 study of sperm viability. Now I will present the findings from 4 studies that examined reproductive hormones. First are the 2 studies in male children ages 6 to 11 years old. Both of these studies use data from the same NHANES cycles. In both analyses, per unit increases in urinary BPS were associated with significantly lower estradiol levels. Total testosterone was significantly lower in the first study, and there was a suggestive association with lower testosterone in the second study. When Wang et al. Analyzed associations by BPS quartiles, they reported significantly lower total testosterone in the highest versus the lowest quartile. The same pattern was observed for the testosterone to estradiol ratio. And for the free androgen index, where one study estimated a statistically significant association, while the other estimated an association that was not statistically significant, but was of similar magnitude. When Wang et al. Analyzed this association by BPS quartiles, they reported a significantly lower free androgen index in the highest versus the lowest quartile. Lastly, both studies reported associations with higher sex hormone binding globulin levels, though the association was statistically significant only in the first study. In the study by Hugh et al., controlled for multiple comparisons, while both studies showed that results were similar after adjusting for other bisphenols. Although both studies analyzed the same data set, there were differences in the study modeling approaches, which likely contributed to the slightly different estimates observed across studies. There were two studies in male adults. The first study by Zhang et al. Was conducted using NHANES data, and the second study by Zhang et al. Included men attending an infertility clinic. The first study reported a statistically significant interaction of estradiol with BMI, such that there was a negative association for normal and overweight men and a positive association for obese men. In the second study, men in the highest exposure quartiles had significantly lower estradiol levels compared to those in the lowest quartile. The test for trend was statistically significant. In the second study, a significantly lower estradiol to testosterone ratio was reported, with a significant trend indicating a dose response. The association was more pronounced in men over 30 when stratified by age. Associations with sex hormone binding globulin was positive in one study and negative in the other. In the second study, there was a significant 11% increase in free androgen index in the third versus the first quartile. Lastly, a significant association between BPS and lower free testosterone levels was observed in the first study, while the second study reported a significant increase in free testosterone, comparing individuals in the third versus the first quartile. Thank you. Dr. Saucier will now present on the coherence among the entirety of the data.
Thank you, Dr. Kaufman. In the next 3 slides, we provide a brief summary across evidence streams, highlighting key BPS-mediated effects on male reproductive function within animal systems, mechanistic evidence identified within these and related systems, and human epidemiologic data. BPS altered sperm development and decreased count, concentration, daily production, and motility in animals and/or humans. Within animal systems with these findings, there was supportive mechanistic evidence, including oxidative stress, genetic damage, apoptosis, epigenetic effects, endocrine effects, blood testis barrier disruption, and interrupted cell proliferation. BPS was associated with effects in accessory sex glands and semen volume. Animal evidence included histological findings in the prostate gland and seminal vesicles. In support of these findings, BPS was associated with lower ejaculate volume in humans. In animal and in vitro systems with these effects, mechanistic evidence included oxidative stress, apoptosis, endocrine effects, organelle effects, and disrupted cell proliferation. Lastly, BPS induced endocrine-related effects. Animal evidence included histological findings of the male mammary and adrenal glands, with abundant evidence of endocrine disruption in vivo and in vitro systems. This was supported by evidence of associations with hormone levels in human children and adults. This concludes our presentation. Thank you for your time and attention.
Thank you very much for those very edifying presentations. We have time now for clarifying questions before going into the committee discussion. So any of the members of the committee have clarifying questions? Isaac?
Very nice presentation. I really appreciated the organization of the presentation. One thing that I found that was missing was this coherence that you referred to. The human data that measures BPS suggests that 90% of it is protein bound. If you account for the last 10%, which should be free, the levels are anywhere between 0.1 and 1 nanomolar in the blood at any given time, given the epidemiological studies. I tried to look up a few of the animal papers to see if they measured blood levels at these really high levels of exposure, but I couldn't find any. So then I went into the mechanistic studies where they actually adjusted the concentrations, and the effects were seen at above 1 micromolar, usually above 100 micromolar, which if you relate that to human exposure, of course, oxidative stress would occur because you're putting in a foreign substance at really high concentrations. So can you sort of assess whether any of the studies that you reviewed had actual serum levels or blood levels in the animal studies?
Yeah, interesting question. I don't remember exactly if we ever saw an internal dose of the BPS on any study. Now, the fact that we have bound or free compounds in humans, is beyond what we can work out. For the other part of the rationale, is on your point that the high dose, assuming to have an effect in animals, that it doesn't reflect a relevant dose for humans, I believe, I will not bring everybody with me, I believe that in science, we are pushing the animals to give us a response without thinking what is the relevant dose in human. So the fact that you see effect at the high dose level, it could be or could not be related to humans. So that's the best approach. That's the model, by definition, is a model. So very hard to extrapolate further than what it is. I don't know if anybody from the staff will want to add more on this discussion, but that's what I have. Thank you. Yes.
Can I comment as a committee member?
Yes, go, please,
So
Martine.
I had the same question, oops, it's not on? It should be on, no? Okay. I had the same dilemma, and I was looking at the methods of the animal studies to see if it justified the dose they used, because there is really two schools. There is a whole series of experiments which are working on the microgram per kilogram per day, which is actually pretty low, and it goes from 1 or 2 to 25 to 50, and they actually see, you can see from the excellent presentation, you have statistical, relevant data, variation, adverse effect. And with the other school, which is more traditional toxico, which go to the milligram per kilogram per day. So I was actually very positively surprised, but not totally surprised, because we know BP has a non-monotonic effect with a microgram, per kilogram doses of very small level being as, and inducing adverse effect, different maybe, but adverse effects, sometimes even worse than the higher doses in the milligram per kilogram range. So I think maybe they inspired themselves from the the abundant literature on bisphenol A, where we know that non-monotonic and danger of a very low doses. That's why we have these two groups clear, of the microgram per kilogram and the milligram. And some teams actually did the studies in microgram per kilogram per day and in milligram per day in the same team. So I thought it was quite good. But going back to the equivalence, of course, it's difficult, but we all follow the model that has been established and documented in a paper, which is sort of based on the surface of the tissues of the species and other factors. And we end up with a miraculous factor, correction factor. It's 6 for the rat and 4 for the mouse. And so I try to sort of apply that to see if, the human BPS level in the serum. So what I got from the various studies were, let's say 0.4 to 2.8, like 3 microgram per liter or nanogram per ml. They had both the same. And that would be an equivalent if you wanted to see what to do in the rat or the mouse would be around, let's say, 3 to 17 microgram per liter for the rat, and for mouse, 2 to 11, let's say, I'm rounding up. So, and some of the studies here do have, like the one in drinking water, they actually express on microgram per liter, and they calculate how much the animal. So some of these ones, the microgram range, I think could be, if you would say that, because the PK shows very excellent absorption and distribution of BPS. If you sort of randomly extrapolate from what varies as doses in the water and what varies in the human blood, this microgram per kilogram it's not the same, but it's what the extrapolation, correcting for species would not be too far off, I think. Of course, the milligram per kilogram is further, but and also one thing that is important is the enterohepatic. They showed in the PK how it recirculates. So it is going to be glycosylate or sulfation, go to the gut, and then the bacteria in the guts are removing the conjugation, and then your free BPS get to go back in the blood again. So there is a mechanism, I think, that you could say that's at least the lower range dose that were studied in many animals. I forgot I put how many. 10 out of the 15 in rat use the microgram per kilogram per day, and 8 in the mouse. So I think it's a good range, and these would be, I think, relevant for human exposure or close. So I'm reassured when I try to massage these numbers, but of course we need, more stringent studies, PK analysis, and measuring the metabolites and everything to really do the equivalent that we already have for other chemicals that have been better studied over the years. This is sort of emerging chemicals. I think that's a problem. I don't know if it reassures you. Try.
Do we have any other clarifying questions from panel members? No? All right. Then we'll now hear from those of us who are designated as initial discussants. So we're going to hear first from Dr. Carrie Berton, Kim Harley, and Sandy Haas on the epidemiology studies, and then we'll hear from Martine Kulte, Charles Plopper, Diana Ayun Kim, and myself on the animal studies. And finally, last but not least, Patrick Allard and Isaac Pessa on the mechanistic studies. So, shall we then begin with the epidemiology studies? And we start with Dr. Carrie Berton.
Okay, thank you. Thank you for the excellent review of the human studies. I'll just recap really briefly, which is to say there were 11 studies, and 5 of them evaluated sperm quality, and 4 looked at hormone levels. And what I want to do is sort of dig a little bit deeper into some of those studies and talk about them. So I'm going to start with the sperm quality as the studies that looked at sperm quality as an outcome. So these were 5 studies. And I just want to sort of comment overall about those 5 studies. They're all cross-sectional. They're from different countries. And there 3 drew on clinic populations such as infertility clinics where they recruited their participants, and 2 were from more nationally representative populations. 3 of them looked at BPS in the blood, and 2 of them looked in the seminal plasma. So I also wanted to sort of distinguish and talk about the 3 that looked at BPS in the blood, sort of separately from the 2 that looked at the seminal plasma. I'll start with the 3 that looked in the blood. And so what was nice about these is they came from different countries. So the Benson paper was from Denmark, Chen was from China, and the third one, Gadya, was from a study in Boston, so the US. And sample sizes for recruitment generally ranged, or for most of these studies, even I'll say all of the 11 studies, typically in the couple hundred, with 1 or 2 of them ranging up into the about 1,200, 1,300, 1,400. So reasonable sample sizes, some of them a little bit on the smaller side. The Benson paper had a sample size of about 500 and drew from the Danish national birth cohort, so a representative population. The downside was that the response rate was really low at 19%. So they tried to accommodate for this statistically, and they basically tried to mitigate any potential for selection bias using inverse probability weighting, and they used a variety of statistical methods that I think made it a more robust paper given some of the limitations they obviously couldn't do a lot about. They used the directed acyclic graphs to sort of inform their statistical analysis and think about and try to adjust for any potential confounding. This was also a study that had about 28% of the BPS detection was below the detection limit. So generally speaking, this study did not find very many associations. They had 1 statistically significant finding, but it was sort of comparing the 3rd quartile to the 1st quartile, not the 4th quartile. So it didn't completely line up like you might hope for in a completely robust study. And that was looking at BPS with the low ejaculate volume. The Chen et al. Paper, I think one of the things going for it is it was one of the largest papers, largest sample sizes. It had a high detection frequency for BPS at more than 83%. It also used repeated urine spot samples. So it was one of the only papers to try and do something more than just a single spot urine. And I know this will probably come up for discussion further, but even so, it was 2 samples that were only 2 hours apart and then averaged together. The sample size was over 1,000. But one of the downsides was participants were recruited from an infertility clinic, and they tried to address any potential issues with that by excluding approximately 200 men who might have had conditions that could affect semen quality. Nonetheless, I think there's some concern about recruiting from infertility clinics when, particularly if those are the studies that are showing most of the associations. I thought that the statistical design was quite robust. They used a variety of regression modeling approaches in BKMR so that they could look at mixtures of BPS and BPA and BPF, but also really isolate the effects of BPS. And also look for nonlinear associations. And this was a paper that did find several associations with BPS or higher BPS associated with progressive motility and the total motility of sperm in particular. And then the 3rd paper, the Gadya paper, was a cross-sectional analysis sort of nested within a prospective cohort of male partners of women who were seeking fertility treatment. So this was but this was a small sample size of only 158. So it really only compared detectable to non-detectable BPS levels and found some associations with semen volume and sperm concentration. And this is also one of the studies that showed worse effects in men with higher BMI. So this is, I think, a consistent theme in some of the population-based studies where there does seem to be a trend toward stronger associations in obese men. So 2 of the 3 studies recruited their populations from an infertility clinic-based setting. I guess that's all I want to say about those. And then the other 2 studies were studies that focused on seminal plasma, which I think is interesting in the sense that we're looking at BPS sort of closer to the target tissue potentially. So there were 2. One saw a statistically significant association with low sperm count and low sperm concentration. And then the other one had non-significant associations, but their directions of effect were consistent. And so the one thing I want to say about the SMART paper, which did not report statistically significant findings, is that this was a paper that really was doing a mixture-based analysis of a lot of different chemicals. And so what they did was actually only report FDR-adjusted p-values. So I think when you think about, since our interest is really just BPS, it's what they don't have at all are their raw p-values. So we don't know if when we're just looking at BPS in their exposure, whether or not they would have been significant. But I think that I take some comfort in the fact that, like, when you look at their results, their magnitudes of effect are fairly consistent. So let's see. So I guess that's sort of my summary of the papers. Those first looking at sperm quality, and then the other papers that I want to just briefly talk about were the ones looking at the reproductive hormones. And so these were 4 studies. Again, there was a really nice summary. I think the comment that's worth mentioning is that 3 of the 4 were in studies based in NHANES. And I think it's interesting that the 2 that looked at the young adults and children showed consistent effects, but the one that looked in older males did not have this, did not show quite the same effects. It did not see an effect with estradiol in particular. I think across all 4 studies, the most consistent outcome is the effects of BPS on estradiol, showing lower levels of estradiol. And then, what else did I want to say about those? They all had pretty larger sample sizes, which was good. And there was one. So then the Zhang paper, the non-NHANES paper, it was actually, in theory, a larger population size of about 1,200, but really they only analyzed 462 subjects after various exclusions, and also after trying to account for, since they were recruiting out of an infertility clinic as well, they excluded a couple hundred men who, for reasons that might, where they thought that they had conditions or what have you that might have affected semen quality. So I think in my take-home conclusions are that there's a limited body of evidence in humans that is suggestive predominantly of associations with some elements of sperm quality and estradiol levels, and that one sort of lingering concern is that some of these associations, they are driven more by the studies that recruited from infertility clinics than necessarily the sort of the more population-based or nationally representative populations. So that's just the one caveat I guess I would have. And overall, they're all cross-sectional studies. There haven't been any really causal studies done. And I guess I'll stop it.
Thanks very much, Carrie. We'll now have a discussion of the epidemiology studies next from Dr. Harley. Kim?
This is on, right? You can hear me? So that was a really good overview and summary. I did want to correct one thing that Dr. Breton said. They weren't measuring BPS in blood. They were measuring it in urine.
Oh, right. I missed that. Sorry.
Which I do think makes it difficult. It adds another level of complexity when we're trying to compare the levels of the doses in animals to what we're seeing in humans. I think I wanted to take a step back and just sort of talk in general about doing epidemiologic studies of BPS is really difficult. I just want to say that of the chemicals that we look at, this is a particularly challenging chemical. We know that it stays in the body for about 7 to 9 hours, I think was what the slide said, which means that most of these studies, except for one, all of the studies took one single urine sample and measured BPS in the urine. And so that's how much BPS was in that individual's body at that exact moment. And if they had done it 4 hours later or a day later, it could have been a very different level. And so that is definitely a challenge in epidemiology, looking at this type of chemical, the bisphenols in general. The other thing is that these are, and also that this is such a ubiquitous exposure, and we're being exposed daily and probably not at the same level daily. So there's really a lot of noise. There's a ton of noise in our exposure measure when we're looking at these urine measurements. We look at urine measurements because the levels are so low in blood that we get a whole bunch of non-detects. So we really have to look at the urine measurements. The other thing I want to point out is that almost all of these studies, all of the studies that we're talking about now, the ones that showed associations with sperm parameters and hormones, were cross-sectional. And I think we need to think about that kind of temporality. Does it make sense that the level of BPS in somebody's body right now is going to be linked to the amount of sperm in their body right now? You know, that exact cross-sectional nature of it. You're making some assumptions, I think. You're making the assumption that the level of BPS that I just measured in you is a marker of sort of longer-term exposure. And I don't know exactly what the critical window is. You know, is it the last 3 months of sperm development? Is it your lifetime? Is it in utero? I mean, none of these studies can answer that question. They can only look at, you know, this cross-sectional nature. So I guess, you know, and we also only have 11 studies. And so there's not a lot of epidemiologic evidence. I want to point out that those 11 studies were actually in 7 populations. So we even have like fewer studies than we think we have. The 2 in boys in N. Haynes, I would just personally consider 1 study because it's this exact same population analyzed by 2 different research groups. So, you know, even though there were 2 studies in boys that found the same thing, I would consider that 1 study in boys that found something. So I guess one of the things that I think about this is it's kind of amazing that we found any signals at all, right? I mean, given how much noise there is in our exposure measure, the fact that we are seeing in the very small number of studies that were conducted, we are seeing consistent findings, I think is something to, you know, to note. The last thing I want to throw out there is in the presentation, I noticed there was talking about the, I think the animal studies alterations in hormones, but it wasn't clear to me if those were, you know, estradiol goes up or testosterone goes down. And I do just want to talk about kind of the directionality of the associations. And we did see quite a bit of consistency in the directionality. I think it was estradiol and testosterone in general were going down. But there was that strange finding of estradiol going up in the obese men. So just, you know, just drawing attention to that fact of like, what's the direction of these associations? Okay, I think that's what I think of right now, yeah.
Adipocytes are very rich in aromatase. So it could be that there is a bit more estradiol in these guys because they just have a lot of aromatase, you know, in adipose tissue. That could be one of the reasons.
I think it's really interesting. The fact that we're starting to see things the fact that people are starting to look at obese people versus non-obese people, I think is really important because we are starting to see different things.
But the impact of metabolic syndrome on male reproduction, I think, is well known, more and more recognized. So it's not surprising.
Thank you. Now we'll have our third discussant of the epidemiology studies, Dr. Sandy Ha.
Is this on? Okay. So I would like to thank my colleague here for the nice summary here and then for your really thoughtful comments. And I would say the benefit of the last person is, you know, we've heard a lot of, you know, of the comments before. So, but I would like to kind of reiterate that, you know, the temporality issue that you brought up earlier, because when I'm reading studies like these, I think about the different, like sort of the Hills guideline for causation, right? And temporality is one of those. And I, you know, as I was reading this, I of course noticed too that like a lot of the exposures were measured once. And there are a couple of studies that measured a couple or 3 you know, time points, but they averaged them. But I guess the assumption is like Dr. Kim was saying earlier, right? We're assuming that these exposures are kind of constant and it's actually coming before the outcome, you know, that's the outcome, for example, the semen quality parameters here. And then the other thing I want to bring up is we have some studies that were comparing people with exposure above the LOD to people with the exposure below the LOD, but these are different across the studies. So then there might be kind of, I guess, like, you know, potential I don't know, I guess like misclassification as we kind of compare across studies, right? Because the LD, the reference line, the break, or like the cutoff line is different for across the different studies. But then for the consistency kind of, guideline for causation, I think Dr. Kim also mentioned is like, given all these issues and the noises that we can potentially, that we think that's going on, we still see some signal, and for some of the outcomes is pretty consistent. For example, for ejaculate volume, right? 3 studies show lower volume, 1 not significant, but the direction of the magnitude of the association is consistent with that too. So I thought that was something to note. And then I think for sperm motility, it's the same thing. 4 of them show lower motility. And then the other one also show the same magnitude of association, but although statistically non-significant. So yeah, those are the only things I just have to add, and I agree with pretty much all the things my colleagues were saying here. Thank you.
Can I add one more thing about the physiology of the system? As you said, we measured BPS at one time point, but if you look at spermatogenesis, it takes a bit over 60 days, from that first spermatogonial stem cell that decide to enter spermatogenesis and goes through a very complex process all the way to get a spermatozoa, which then has to stay usually 2 weeks in epididymis, where it's maturing and acquiring that motility they are going to measure at the end. So what they see when they measure that BPS, and what they see is the result of something that took place, and because we're exposed constantly to low level, for over these basically 2 months, and because nature has done things that we are not synchronized, so that if a man is exposed to a chemical, not all the germ cells are going to be damaged because you want reproduction to continue for the species. So nothing is absolutely synchronized. So you have cells in all these different stages of development in the spermatogenic process. And so you don't know, some of the stages are known to be more susceptible to some chemical than the others. So you don't even, from this study, can say yet which was the germ cell level that was a primary target, or maybe it was a secondary target to the Leydig cell or the Sertoli cells that you nicely described. So it's a very complex system, and we just see that one snapshot of something that has happened. At least maybe for the sperm you are measuring, it's 60 days prior, or like 80 days prior if you add the time it stays usually in the epididymis. But in reality, it's lifelong, because that comes from a spermatogonial stem cell that was formed in that human baby in the first few months of life, like around 3-5 months of life. So what you can see at the end in that adult guide might result from when he was a little baby and the spermatogonial stem cell didn't form exactly following the right process to get, a sperm at the end that would acquire the perfect motility and all the functionality, like, fecundity and so on. So it's a complex system. So I think, as you say, it's actually surprising and a bit concerning that we are able to measure statistically significant responses in these human studies.
Thank you very much. Any additional comments? Yeah, Patrick?
It's actually not a comment, but a question to the AP people. I'm wondering, as you were reading the studies, how the investigators try to parse out BPS versus all the other bisphenols, and how they adjusted for that, and also not just BPS versus, but also the cumulative exposure to these different bisphenols that, mechanistically speaking, in theory, can all have estrogenic activity to different extent, but so you could think of the cumulative impact of all these bisphenols at the same time. So yeah, I'm just wondering, when you look at the studies that way, BPS versus the other, or BPS plus the others, how people really took care of that aspect of the concerns with regards to BPS.
Mary?
Sure. I would say quite a few of them, I'm not sure I have the exact count right this second, use BKMR or use a statistical methodology to do exactly that, to try to control for the other, like, BPA and BPF, so that they can confidently say this is the effect of BPS, holding the other two constant at their median levels. Or they used like a linear regression model and they adjusted for one versus the other if the two weren't really highly correlated. I know at least a couple of them found similar results for BPA as for BPS in looking independently at them. So I recall that as well. So there in the epi literature, there's an increasing trend for the newer studies to take mixtures-based methodological approaches, specifically for these chemical classes that are very similar. So if anybody else wants to add in or remembers, exactly how many of them did that, feel free. But
yeah.
I'm pretty sure that every study that looked at BPS also looked at BPA and most looked at BPF. So all of them kind of were accounting for, were at least acknowledging the other ones. I think only one of the Siemens studies did BKMR. You're agreeing with me, Sandy? So which was really nice to see. I was glad that they did do that. And as you say, that's becoming more and more the trend. Some of these studies also were looking at more than just the bisphenols. There were certainly a bunch of studies that looked at just a laundry list of, well, mainly it was the phthalates, the phenols, and similar chemicals. But yeah, exactly the ones we measure in urine.
Isaac?
So I just want to make sure. So they actually had measures for BPA, for example, which according to figure 2 should be on average about the same level as BPS now. They actually made the measurement and then controlled for co-exposure.
I would ask somebody to just confirm that, but I know they all looked at that. But I will say, and we should go back and check, in most of the studies, the BPS levels were quite a bit lower than the BPA levels. I mean, in some studies, they were an order of magnitude lower, if I'm remembering correctly.
I'm just going on figure 2, the latest 2015. It shows that if you read across, the studies suggest that they're about the same level in 2015. Right? Am I missing something here? I may be
This is figure 2 from what?
Yeah, figure 2 in the document that was prepared.
Depends on when the studies were conducted. In the paper. Further discussion, or are we trying to find the?
I mean, I think, are you referring to figure 2 in like the PDF that was?
Yeah.
Oh, okay. So, correct me if I'm wrong, but I thought that data came from like the California biomonitoring so we may be sort of apples and oranges in the sense that if that, versus the levels in each individual study, which also are more recent and like from 2019 to 2021 maybe, but I haven't pulled up the table yet, or the figure.
Martha?
I was just going to say, in the figure in the hazard identification document is from a paper that looked at several different populations, different N. Haynes groups and marbles, and but it's unclear that each of these comparisons are looking at the same populations. As it's a broader swath of multiple populations as opposed to these studies you're talking about right here, where they're measuring it in a finite number of people, both all these different chemicals. So.
Right, but the values seem to be converging. Just take the data. Yeah. I had one question on BMI. Isn't there an effect of BMI on sperm quality irrespective of exposure? And did they control, the epi studies control for that? I don't know how they would.
I can speak a little bit to it. Yeah, I think a lot of studies did control for BMI, but some of them also kind of stratified by BMI too, and that they found that the effects were stronger among men with BMI, if I believe correctly, over 25. So that's...
The BPS effects.
Right. BP, yeah.
Questions? Sorry.
I'd just offer a clarification. So there is a crossover in general between the production and use of BPA and BPS, as was noted in the HID, the hazard identification document. And the figure that you referred to does come from different studies, different populations, and they are on different axes. So, you know, the relative difference is one thing, the actual measurement is another, right? The levels are different. And the study populations come from different times. The earlier studies obviously would not have been showing as high an exposure rate because BPS wasn't really substituting for BPA until more recent times. So just to offer that clarification. If there are any other questions, yeah?
Well, just to follow up on the relative concentrations of BPS versus BPA in the studies that we looked at, I've just pulled up a couple that I can easily find. The geometric mean was about 0.3, 0.4 for BPS in most of these. And BPA in this study, one study from N. Haynes, BPA was 1.4 as opposed to 0.4. And let's see, in the other one, BPA was 1.8 compared to 0.37. So BPA levels are considerably higher.
I could add, if you look at the figure from the general presentation, that compared in the urine of a pregnant woman, and you can see very clearly that the BPA in all these studies from different studies, it's all, yeah, usually BPA is 1.5 times higher than BPS. Like it's in all the studies is consistent. So you have a decrease of BPA and an increase of BPS, but even though, like in 2015, when the latest year, you're right, the BPS is still much lower, but it's increasing, and it will keep increasing as more restriction is put or applied by the companies for BPA. So it's even more amazing that they find association with something that it's still in a lower, exposure level for humans.
No further raised hands. Then I'd like to turn now to the animal studies. And so we will start out with Dr. Martine Kelty.
First, I want to thank Dr. Saucier for a very excellent summary of all these studies, because I was trying to organize myself, and you have done it, so it's perfect. So I don't have much to add up, except, I was actually surprised that there were like 14 studies in mice, 20 in rat, 1 in hamster, 1 in gerbil, and 4 in fish, for a product that really has emerged quite recently compared to others. But I think we are basically now functioning of a lesson we learned from BPA and are more proactive, maybe, people are more proactive in studying the potential risk of these substances. If you look at it, so I mentioned already that it was surprising for me that there were really 2 types of strategies looking at the lower exposure doses of a microgram per kilogram per day, and that could be the classical Toxico 28-day for toxicology study, but also some went further, to several months, and in logic, you should be more than 28 days if you want to study male reproduction, because that's not enough. As I just said, the cycle being already, a bit over 60 days long, if you do only 28 days, you are not assessing the whole spermatogenesis, for example. So for steroidogenesis, for Leydig cell androgen production, it's easier because they don't follow a cycle like this. Of course, there's more testosterone in the morning, it's regulated by LH, but it's still, sort of more permanent. But the 28-day don't capture enough, the potential adverse impact on male reproduction for at least sperm formation, for spermatogenesis. So it's good that a number of those went beyond the 28-day. classical toxicology requirement. Also one surprise I had, it's how around half of them were actually using adult exposure. In the toxicology field, very often we know that fetal, neonatal, up to puberty for reproduction are more sensitive periods. And so we tend to look more at the younger age of exposure. But here they were looking at the adult, although, as I said before, the adult is a result of lifelong exposure. And you are just looking at the final result the day you decided to do your study on this patient. But so there were 2 on lactation, 2 that were covering neonatal periods, 2 covered puberty, which is not very often, and it's a very sensitive period where the reproductive system is totally remodeled. Your hypothalamus pituitary start to have oscillatory production, and everything is different. But very few people really study puberty, whereas it's really a susceptible period. So there were 2. That's not bad. 8 was gestational type of period or gestational lactation, and 1 went from neonatal age to adulthood. So it sort of covered a broad range of ages, of a type of exposure, and as I said, 1,000-fold difference range in dose of exposure. Besides that, the difference, it's sort of the outcomes are pretty homogeneous. You can have, they showed actually what is, I think, take-home message is the microgram per kilogram per day exposure ranges gave basically the same type of adverse phenotype as the milligram per kilogram per day. And that's typical, it's not surprising, it's typical of a non-monotonic endocrine disruptor where you have adverse effect at both low dose and high dose. The mechanism might be different, and maybe Dr. Alla will discuss that. You might have totally different type of responses in your cells and your tissue at the very low dose and the higher dose, because they're not very high. They are still, in the range relevant for human exposure. But the end product, which is testosterone level, spermatogenesis, sperm count, and so on, they are pretty similar, which should be a concern for us, because we see adverse response at very low doses that if you would be, the EPA or somebody doing a classical toxicology study where you look at your very nicely, dose response, linear dose response, and the linear range where, the lower dose should have a lower adverse effect than the higher dose. This is not true for hormones, and this is not true for endocrine disruptor. So I was positively surprised that these studies, although there are not many, sort of give a reflection of the challenges of endocrine disruptor, where you have these low doses having adverse effects similar, and these are the functional role of a male reproductive system, make androgen and make sperm. So both are affected by the low dose and the high dose, and I think that's a concern. So as you described, sperm count was decreased in most of the animal studies, and or sperm motility, increase of abnormal sperm in a variety of the studies. Testosterone, either in the circulating testosterone or intratesticular testosterone, in most of the studies were also decreased when it was measured. And the number of abnormalities at the level of the seminiferous tubules, where the Sertoli and the germ cell are sitting, and that's where spermatogenesis happened. Vacuolization. So one only little artifact that you mentioned, that I think this, we sort of all agree that it's an artifact of a method. When you see this increase of interstitial space, this white space increasing between the tubule, your interstitium, you can still see it's there. And it's just, somehow you have an enlargement of the space between, they detach from the interstitium, basically the tubules. And we see that a lot, and it's partially a technical issue, but it's somehow more often in the treated sample, which means that it could be, it's just an hypothesis, I don't know if anybody studied that, it could be that the interaction between the interstitial cell and the tubules might be affected, and that's why it's, it's pulled out more easily. But it's not the interstitial space that enlarged, because you can see the interstitium, if you measure it, it's still the same dimension. It's just that empty space between the tubule and the interstitium that somehow they detach more during the processing of your sample for analysis. So that's the only thing. But it might be, some type of real cause to that. I don't know. But so the paper that mentioned that, yeah, I would not consider that one specific. There were many other very strong, outcome to consider. So we don't need that one. And I wanted to mention also one thing I was surprised, it's the increase of adrenal cortex thickness and effect, and it could actually have a consequence because I thought, why are we going to, measuring the, but in reality, we know the adrenal cortex, it's not only that they do androgens, but the cortisol has an adverse effect on testosterone production. So we crosstalk between the two tissues. So if you have that increase, hyperplasia of the adrenal that they measured, I don't think, I cannot remember if they measured cortisol, but to have a changing in glucocorticoid in the sort of a hypertrophied adrenal cortex could have an impact on at least testosterone production. Glucocorticoid are known to decrease testosterone production. On the other side, thyroid hormones have a positive effect on, testosterone production. So the effect that they measure in thyroid might have an indirect effect on the reproductive function also, at least on the, steroid production. Yeah, I think that's mainly what I wanted to say. And I think the data, although it's emerging, concern and emerging chemical, there is actually an accumulation of data over the last few years that support being concerned, to my opinion, if we put that together with the human data. That's it. I don't know if I'm supposed to say that or not.
Right. Thank you very much, Dr. Kelty. Our next first discussant of the animal studies will be Dr. Plopper. Charles.
Thank you. I want to thank both Drs. Park and Souther for their summary. You used up about 3/4 of what I was planning on saying, so that's good. And she finished off the rest of it. The one concern that I had here that I would just like to spend my time on is the fact that we need to remember that the whole process of spermatogenesis, a large part of it is in the uterus and the fetus, and then a short part postnatally, and then you go through the process once it's all been established. Then from then on, it's all the generation of mature sperm. And one of the things that I thought I would do that when I was going through this, I expressed for other people's concern is what happens with exposure at different time points, and is the effect essentially the same? So I went through and analyzed these studies, and I'll take a few minutes. I looked at the ones that were exposure was only gestational, and then there were some that were gestational with a little bit into the lacrimal phase. In both of these phases, it's the exposure of the mother that's the key issue. And this brings up one of the things I wondered about with the epidemiology is that you can't really assess the effect of the exposure on the mother of the studies that are being evaluated, so you don't really know what this effect is. And then finally, what happens at the pubertal time and prepubertal, there's a major changes, at least certainly in humans, if not others, in the way the testis organizes sperm and does all the rest of this. And then there are the adult studies where it's just generating new sperm. So if I have the time, I'll take a few minutes and just look at that. The first is the gestational studies. I found 4 studies that seemed, I will just say right now that the only ones I looked at were ones that were peer reviewed, because I looked at the others and I was not impressed. I did not, just, that's the way it is. So there were 2 in rats and 1 in mice where the assessment, the exposure was stopped at birth. So the mother was exposed at ranges, high ranges and low ranges like you're talking about. And of course, unfortunately, we don't know what the animals received, but when we looked at their approaches at adults, most of these were assessed by the time they were adults. Every one of them had the disarrangements in the the seminiferous tubercle organization that was already mentioned. And when the one that looked at the effect on the sperm, it was the same thing. Low counts, low motility, all sorts of mutations in that process, which said to me that this was likely that the whole effect could it just as easily be for once the exposure occurs in utero. And then there were 5 studies that looked at the exposure, which is only in the lacrimal phase. In other words, from birth until the lacrimation stops, and all of them found essentially the same results. If they had studied the seminiferous tubule, it was damaged and disarrayed and went through all of the processes that were already mentioned that show that it's not functional. And the same for the ones that, because most of these were then sampled, quite a few tested while they were almost adults, the ones that checked sperm found the same problem. Motility's down, count is down, mutations are up, irregularities, a lot of abnormal sperm. And the same is true for there were 6 studies that were prepuberal. In other words, as soon as the animals finished lactating, they're using lacrimal, so then they were exposed then. The results were exactly the same because when they were looked at, somewhat changed if it was assessed after the 28-day exposure period, but if it was allowed to go on until, and then they were tested when they were adults, they all had this, they all never exposed again, exposed at some of them at very low levels. I was quite surprised. They all showed decreases in sperm motility, and the number was reduced, and the counts were reduced, the viability was down, and for the testis, it's what was already outlined. The germ cells were mixed up, there was vacuoles, and the interstitial spaces, there was a marked change between seminiferous tubercles that were normal and occupied most of the testis, and the interstitial space was small. It's only where the key Leydig cells were set up and normal. Well, the change was complete. So it was disrupted. The whole surface was disrupted. And they were this is only puberty. Never exposed again. You know, somewhere between 60 and some of them were more than 100 days old. There wasn't any, it was still, the change was still there. And then finally, of course, all the adult studies, which there are a large number, and everybody's already summarized them, but I'll just re-emphasize that when you assess the testis, there were 8 studies that looked at it, and they all found the same distribution changes and pathology in the epithelium of the seminiferous tubule. And the ones that looked at sperm effects found the same thing. Decreases in motility, decreases in count. In fact, one of the things that disturbed me the most was that some of these studies found virtually no sperm, or even the last 4 stages of sperm development. There were none in the lumen, either of the seminiferous tubules or the epididymis, which suggests that this is even at low doses, this can be a very marked damage and a disruption of a very key process. And I think that, I think that's about all I wanted to say. There was one study that did multi-generational, and you're all familiar with it, but it was treatment 3 times with breeding in between, and it had the same effect. And then there was another one, which I thought maybe we'd just finish with that. It brings up what the issues before. The exposure was done via the mother to the first generation, and the first generation was mated, the second generation was mated, and then the third generation at postnatal days 6 and 60 were assessed, and what they found was that there was changes in the development of the sperm, and that the testis was disrupted. So it means that this is something that we're questioning. It's something that may be inherited as well, because there were 2 generations of parents that didn't receive any exposure, and their offspring still, their great-grandson still didn't work. So I guess I would be, my comments, everybody's covered most of the other issues that I had on my stack of lists here. But I think that the key thing to say is that the exposure can be occurring at any particular time once the epithelium in the seminiferous tubule begins the process of forming sperm. And this can be occurred, and it doesn't matter when it happens, when the exposure occurs during this process. It seems to be something that lasts for a long time. And I think that readdresses, it was so funny because when I read the epidemiological studies, I just thought I didn't know what I was talking about, because they didn't make any sense sometimes the way they were discussing. But what happens if it was the mother that was the problem? And then this you're assessing an offspring, and it may be that was the grandmother that was the one that caused the problem, is what you find now. So I just think that that's my comment on the animal studies. I think they pretty much outlined how susceptible the reproductive system in males is to exposure to BPS. And I guess I'll stop that and answer questions. Sorry about that.
Thank you very much. Does anyone have any comments, questions before we?
Can just add for the multi-generational or transgenerational, there were some data on epigenetic genes and markers in a bunch of these studies. So it's not surprising. They looked actually at potential, disruption of the like change in epigenetic marks and enzymes. So I think that's probably where it stems from. Right. The sperm is carrying basically epigenetic variations.
Kim?
That was such a great presentation, and I'm so glad that you did that, because I had a question and I thought, well, nobody's going to have done the research to know the answer to this. And I think you did answer it. I just want to confirm. When I look at the epi studies, when we look at the sperm effects, we're looking at, the animal analog would be adult exposure at very low doses. And what I heard you say is that you see in the animal studies that there were several studies that did low-dose exposure in adults, and you did see effects on reduced sperm count and motility and things. Is that correct?
Yes, that was a measure of, they couldn't do it in the ones exposed during gestation unless they waited long enough, because there wasn't going to be any sperm in the normal at birth. But once the lacrimal period is over with, then it's during that part that you get to the final stages of spermatogenesis. And yes, regardless of when the exposure time was, and even in during gestation, if the assessment was made when they were adults, which meant they went through the entire maturation, productive period, and then yes, there was still negative impact on the sperm.
And if they were only dosed in adulthood, you also saw negative impact on the sperm?
I'm sorry.
If they were only dosed in adulthood, were there any that were only dosed in adulthood, or were they all dosed, gestationally?
Well, it was gestation, there was post-gestation lacrimal, there was puberal, and then there was adult.
So they were dosed continuously the whole time?
No.
Okay.
Only one study did that, and it did it. The problem with that study, why I didn't want to discuss it, is because the strategy they used was to expose both the females and the males and then breed them every cycle. So they did, yes, it was negative, but it could have been just because it was the parents that were that way on the next generation. But no, there were none of them, there's only one study that looked all the way, exposed all the way through. And I didn't really want to discuss it because I don't think it matters, because all I had to do was be exposed as gestational period, and they're going to have this disruption anyway. Okay, does that make sense?
Yeah, no, I just wanted confirmation that there were studies that were low-dose adult-only exposures, because that's what we see. Yes. That's basically what we're measuring in the EPI studies. Yes. So I just wanted to make sure that those were.
There were, and they showed the results. Either the ones that looked at the seminiferous tubule, yes, they're just completely disarranged. I was quite shocked the first time I looked at some of these studies, and they say, well, they weren't fixed well. Well, that's fine. I spent my whole life dealing with fixed tissue, so I could look at the ones that aren't so good, and they still had the same problems. In fact, it was quite shocking to me to see that some of the lower doses exposed in gestational phases, there was absolutely nothing that looked like a mature sperm in the lumen of any of the tissue. So that meant that this could be a long-term effect, and it could be very low. And how do you know how many times the mother of somebody that's being assessed as an adult was actually exposed to this at high levels? And, you know, it could be, I hate to say it, but it could be a mother that drank 4 bottles of plastic water with plastic in it every day the whole time she was pregnant. The kid's going to have a major exposure level. And now we know, at least from the animal studies, that this effect lasts. Even though it's, in fact, I was quite surprised at one of these studies, the study I mentioned where it was multiple exposures, but the exposure was only at the F1 generation. It still disrupted the sperm generation and function in the great-grandchildren. If you can call mice having great-grandchildren, but it seems that that some of these, we don't know what the mechanism, well, we're going to find out about the mechanisms. We got the experts here to tell us, but it looks like that once there's a disruption in the germinal epithelium, it's a problem that lasts.
But
sorry.
I have a comment for the epidemiological studies. When you say it's an adult study, you are studying what happened at that time point when you collected the samples and you collecting the sperm and measure the BPS, but that probably is not an adult exposure. It's a lifelong exposure that you measured in an adult person, except if you can, I don't see how you could, isolate the people who were never exposed to BPS before the time you study. I mean, except if they have a dramatic change in their lifestyle, most likely they were exposed before you did your epidemiological studies. So it's just a reflection in adulthood of a lifelong type of exposure. At least, since the time that BPS was released and used in a number of consumer product.
I think the only comment there is that since BPS is a relatively new compound, that in the human studies for everybody who's looking cross-sectionally now is still cross-sectional, but it's not likely that they had in utero exposure if we're looking at 30 and 40-year-olds.
You're right. So it really like a 10-year.
I was just going to bring that point up as we got to look at the.
You're right.
And there were no studies that, like at this moment in time, are looking at prenatal exposures, which could conceivably occur now, right? But that wasn't any. There weren't any.
I mean, we know they occur because they measure in the urine of pregnant mothers.
Yeah, so. Sure, exactly. But, yeah.
But yeah, you're right. Since it was used like in the last 10, 15 years or something, so at least we know it's, what we see now transgenerationally in animal, we'll have to wait for the next 20, 30 years because people don't do children so young now. So we'll have to wait many more years to see that in human.
Yeah.
Do we want to wait?
One more comment?
Yeah, I know, sorry. Just the point that the in utero exposure is really important for epi studies, and we can do those. We don't have any yet, but we did actually review one study, the Generation R study. They didn't look at sperm outcomes. They looked at cryptorchidism and hypospadia and timing of puberty. But theoretically, if they could bring their kids back in, their kids must be late teenagers now, these studies can be done, and they need to be done.
They should be done, yeah.
Thank you. That was great discussion. Our next discussant for the animal studies, again, will be...
Ask one question. Can I ask one more question? I think I know the answer to this, but I just wanted to check. In the animal modeling world, are there any... Do you ever look at obese animals? So, like, is there the possibility of having looked at BPS exposure treatment among obese animals, just given the human?
It's possible, they are model, but the people who who want to do that. Either they have to be NIH employees, but they have the money to buy the animals, or they have to have obtained a grant from the government, which means there must be an interest in the government to fund these people.
One other thing, though, is that a lot of these studies, I didn't bring them up because I don't necessarily believe it, but they test toxicity by measuring the organ weights, and depending on how the whole animal responds, the weight could be different. And we never thought about doing that, but there are ones for which the weight goes up and ones for which it goes down. And it would be interesting to see, is that effect the same on both? And both, basically, that hasn't been discussed, but it could have. That's a very good point. But it's very difficult to make fat animals, I can assure you that.
No, I mean, there are models that exist. It's just
Yes.
you have to treat your obese animal with BPS, and you just have to decide to do the experiment. But
Yeah.
it's feasible.
All right, Diana,
I don't have any additional comments because my concerns were looking at the concentration, exposure levels, and that Dr. Colty covered that, and then also with the timing of the phase of exposure, and Dr. Plopper covered that, as well as Dr. Park for the general overall. So I don't have any additional comments. Thank you for the exhaustive discussion. Yeah, and I'm the last person, and I agree. I think that was a great discussion. And, I mean, just overall, I think one of the remarkable things about this data set was the relative consistency that's already been mentioned among the, the different endpoints that were affected at very low doses that I think are more close to human relevance, as well as at the higher doses. So I don't have more to add than that. And I think the next group of discussions will be about the mechanistic studies, but since it is basically noon, should we take our lunch break now, or? Yeah, okay, all right. And then reconvene in 1 hour, or 1 o'clock? Or 45 minutes? Oh, that's right, because we don't have to go outside. Okay, thank you. All right. All right, so we'll reconvene at 12:45.